Hello, my name is Joel Schneider, and in this lesson I'd like to talk with you about surface integrals and how they relate to double integrals, which we already know. We'll start with looking at surface integrals and understanding the concepts behind them. I will go through a couple of examples of surface integral calculations. Okay, so let's start with looking at what we already know about double integrals. Double integrals, if we look in three dimensions, we're integrating over a region in the xy plane, represented here by this blue shape. Since we're only in the xy plane, it's a two-dimensional shape. We only have 2 degrees of freedom. In addition, we only have two variables changing. Z does not change whatsoever inside our region. It is completely irrelevant. X and Y are the only variables that change. This means that we can only move freely in two directions. Our position along the vertical direction, or the z-axis, is completely determined by our locations in x and y. In other words, the shape that we are confined to is a two-dimensional shape. Now let's compare this to surface integrals. In surface integrals, instead of integrating over a flat region in the xy plane, we're integrating over some generic surface that can be anywhere in 3 space, like this section of blue surface here. In this situation, we also have 2 degrees of freedom, because as soon as our x and y locations are determined, our z location is fixed. The shape that we're integrating over is still a two-dimensional surface. It's simply in 3 space this time. However, unlike with double integrals, now we have 3 variables changing. X, y, and z all change depend on where we are on the surface. This complicates our situation somewhat. We can't calculate the surface integral straightforwardly like we did with double integrals. With double integrals, we only have 2 integral symbols. How can we use that for surface integrals if 3 variables are changing? Instead, what we'll have to do is do a change of variables in order to convert our surface integral into a double integral. We can visualize this by taking our surface and using a projection to move it down into the xy plane, so we can use a double integral like we are already accustomed to doing. So now that we know the background on surface integrals, let's move on to looking at how we can actually calculate them. Surface integrals are usually one of 2 forms. There is the flux form, which looks like the double integral over a surface of some vector field dotted with the normal vector times the surface element. What this essentially does is it looks at every surface element ds and finds the component of the vector field that is in the same direction as the normal vector, and then we add this up over the entire surface. This calculates the total flux of a given vector field through a surface. The other form of a surface integral is a much more generic form. It is simply a scalar function of 3 variables times an element of surface area. We usually use this type of surface integral when we're trying to integrate some scalar quantity over a surface. Although these 2 forms look very different, we'll find out that the way we evaluate them is actually very similar. Because of this, we'll simply start with the flux integral, as it is the one that we usually use most commonly, and along the way we'll discover how we can solve the scalar surface integral. As a starting point, let's begin by looking at the normal vector. Well, if we're trying to find the normal vector to a surface, we already know a method that we can solve this problem. We can use the gradient. We know that the gradient of a function is going to produce a vector that is perpendicular or normal to the level curve. So we can use the partial derivatives in the gradient operator on our function that is our surface in order to be able to find the normal vector. If we have a function of our surface that is in terms of x, y, and z, then our normal vector is going to be f sub x, f sub y, f sub z. We also looked at a special case where we already have the formula for our surface explicitly given in terms of z equals a function of x and y. In this special case, the partial derivative with respect to z ends up being -1. Either of these vectors gives us the normal vector, and if we divide by its magnitude, then we can find the unit normal. Once we have our unit normal, we can take the dot product of our desired vector field with this normal vector. This will give us a scalar function of x, y, and z, just like we have in our generic form of the surface integral. The only step that we have left in converting our surface integral into a double integral is to rewrite our surface in terms of area. To do this, we need to find ds in terms of dA. We need to perform a change of variables that represents the projection we're trying to do. If you look here at these two different elements of surface area, ds, when we project them into the xy plane, we'll get exactly the same dA. But you can see that because the slope of the surface is much different, the area in the surface, ds, of the right surface element is much greater than that of the left. So our change of variables is going to have to take into account the angle of our surface. To do this, we can find the Jacobian. If you recall, the Jacobian is a scaling factor that we add into our expression for our integral when we're trying to convert from one variable system to another. So we can rewrite ds as our Jacobian times dA. If you recall from class, we actually derived what this scaling factor is. By using the angle of the surface, we found that the unit normal times ds is equal to plus or minus the vector minus f sub x minus f sub y 1. This was for the case in which we had z of our surface explicitly given as a function of x and y. In the case when our surface is given as an implicit function of x, y, and z, we modify this slightly to get plus or minus vector fx over fz, fy over fz, 1. Now, since this was just a Jacobian scaling factor, we have to make sure that we include our dA. So we have each of these vectors times dA. Now that we have found the normal vector times ds as a function of the variables given to us in our surface, we can also calculate the scalar ds. Since the unit normal vector has magnitude 1, we can take the magnitude of the vector we found above and we'll be left with ds. We can use this to solve the scalar form of the surface integral that we mentioned earlier. Sometimes the quantity n hat ds is abbreviated by ds with a vector sign over the s. Both of these two representations are completely equivalent. Now we need to deal with the plus or minus symbol that we had in our n hat ds above. By convention, the normal vector on our surface is usually oriented such that z is positive. However, it's usually good to delineate whether we're asking for upwards flux or downwards flux just to avoid confusion. However, sometimes we are asked to find inwards or outward flux. These don't necessarily have some direct relationship between upwards and downwards. For example, if we look at this upper half of a hemisphere, the inward flux points downwards, and the outward flux points upwards. So when problems are referring to inwards and outward fluxes, we need to pay particular attention to which direction our z is pointing. So now we have every piece we need to be able to calculate our surface integrals. So let's outline the general problem-solving approach to solving a surface integral. The first step is to sketch a picture. It doesn't have to be terribly accurate, it just needs to help you be able to visualize what the problem is and what areas we're trying to find integrals over. The next step is to identify the surface you're interested in and figure out what its boundaries are. Oftentimes these boundaries and their equations will be very helpful for us once we've projected into the xy plane. The next step is to use the expressions we found earlier to calculate n hat ds. You also need to make sure that after you've calculated this, you identify which direction is the correct z direction based on the context of the problem. Next, you'll project your surface that you're interested in into the xy plane, and using the boundaries that you know, figure out what the boundaries of your region are in the xy plane. Plug in your expression for n hat ds that we calculated earlier, and then you should be left with a normal double integral in the xy plane that we can evaluate as usual. So let's try and apply this problem-solving approach to a couple practice problems. The first problem is to find the upward flux of the vector field f equals xi hat plus yj hat plus zk hat through the surface S, where S is z equals 4 minus x squared minus y squared, only above the xy plane. So our first step is to draw a picture. So let's start with that. If we draw in our axes here, we know that since we have 4 minus x squared minus y squared, that as x and y get very large, our z is going to decrease to negative infinity, and that our maximum will be when x and y are both 0. Because the x and the y are each squared, and we have no square roots anywhere in here, we know that this is a paraboloid. So we can sketch in our paraboloid here with maximum at 0, 0, and our boundary is going to be when the surface intersects the xy plane. This is when z equals 4 minus x squared minus y squared is equal to 0. This means that our boundary is going to be x squared plus y squared equals 4, which is a circle. In addition, we need to make sure that we note what direction of flux we're looking for. We're trying to find the outward flux, denoted by this orange arrow here. Since regardless of our location on the surface, the outward flux always has a positive z component, that means that the normal vector we're looking for has a positive z component as well. So if we calculate our n hat ds in the next step, we know that we have negative fx negative fy 1 times dA. If we plug in our function of our surface for f, then we can solve to be 2x, 2y, 1 times dA. Now we need to look at the region that our surface makes when it's projected into the xy plane. If we draw our diagram again, the projected region is going to be this purple area at the bottom. We already found the boundary was a circle, so our projected region R is going to be x squared plus y squared is less than or equal to 4. So if we take our surface integral, double integral over the surface, of f dot n hat ds, we can plug in all of the values we have and turn this into a double integral over the region R of the vector x, y, z, which is our f, dotted with our vector 2x, 2y, 1 dA. If we multiply this out, we'll get the double integral over the region of 2x squared plus 2y squared plus z times dA. Since we're in the xy plane, we don't want a variable z in our expression. We only have variables x and y. So we will need to convert our z into x and y. We use the function of our surface, which we already found, because everywhere in our region, z is always satisfying this relationship of z equals 4 minus x squared minus y squared. If we plug in this expression for z and simplify, then we'll have the double integral over the region of 4 plus x squared plus y squared times dA. Since the region we're integrating over is a circle, it seems natural to convert this to polar coordinates so that we can evaluate it more easily. If we're converting it to polar coordinates, then x squared plus y squared is equal to r squared. So our integrand will be 4 plus r squared. dA in polar coordinates is r dr d theta. For a circle, since we have x squared plus y squared equals 4 is our boundary, that means the radius is 2. So our radius ranges from 0 to 2, and our theta ranges from 0 to 2 pi. If we integrate this with respect to r, and evaluate, then we'll be left with the integral from 0 to 2 pi of 8 plus 4 d theta. This simplifies to a final answer of 24 pi. Okay, let's try another practice problem. Let's say we want to find the flux of the same vector field, f equals xyz, out of the surface x squared plus y squared plus z squared equals 4. We can graph this in 3 dimensions. We always want to start with a picture. And we get a sphere of radius 2. Now since we're trying to find the flux outward, that means the normal vector we're looking for are these 2 orange arrows here. However, because our shape is a sphere, we notice that we don't have a consistently upwards pointing or downwards pointing normal vector. Depending on where we are on our surface, Sometimes outwards means up, sometimes outwards means down. In order to simplify our problem, let's try using symmetry. If we look at the top half of our sphere, you can see that the vector field has a positive z component, as does the normal vector. If we look in the bottom half of the sphere, our vector field is exactly the same as it is in the top half of the sphere. However, the z-coordinate is negative, so it's been reflected over the xy plane. The same thing is true of the normal vector. Because it's a sphere, the normal vector is exactly the same in the bottom half as it is in the top half, just with a negated z-coordinate. So the flux over the top half of our sphere is going to be exactly the same as the flux over the bottom half of the sphere. So if we want to calculate the overall flux, what we can do instead is calculate just the flux over 1/2, and then multiply by 2 at the end. Since we can choose whichever one we want to figure out the flux, let's just say we choose the top half. In this case, our normal vector points up. It also points radially outwards since this is a sphere. That means that our normal vector is going to be equal to xyz. However, we need to make sure that we have a unit normal vector. So in order to do this, we have to divide by the magnitude of our normal vector. Since we're on the surface of a sphere with radius 2, that means the magnitude of our vector is always going to be a constant 2. So now we're going to work with actually calculating our surface integral to find the flux. Instead of converting into a double integral, let's see if we can continue to use symmetry to simplify our calculations. Instead of figuring out n hat ds in terms of dA, what if we can just explicitly find it? We've already calculated n hat by itself. Is there a way that we can calculate ds by itself? Well, we have a sphere, and it seems natural to explore our sphere in spherical coordinates. Let's draw out what a differential unit of volume looks like in spherical coordinates. Here is our small unit of volume, and we know that ds that we are looking at, since we're on the surface of a sphere, is this curved surface here. We also know that the perpendicular length to the surface is going to be d rho, since that's the radial direction. So we have something that is roughly cubically shaped, with one surface of surface area ds and a height of d rho. We already know that this differential element of volume has volume rho squared sine phi d rho d phi d theta. We also know that the volume of a cube is the surface area of the base times the height. So if we want to find the surface area of the base, or ds, we can take dv divided by d rho. That means that ds is equal to rho squared sine phi d theta. Now let's see if we can move forward with actually calculating our surface integral. We have the double integral of f dot n hat ds over the surface. Well, we know that xyz is equal to our vector field, and we found that our normal vector is equal to 1/2 xyz. So if we take the dot product here, we're going to get x squared plus y squared plus z squared. Since we know that we're on the surface of a sphere, we know that this quantity is equal to the radius squared, so 2 squared. So we have the 1/2 still out front, then the 2 squared from product of our two vectors, and now we can substitute the expression we found for ds. However, since we're on the surface of a sphere, we know that rho equals 2, so we can plug that in as well. If we're looking at a constant theta, what are the ranges for phi? Since we're only looking at the upper half of a sphere, we know that phi ranges from 0 at the z-axis to pi over 2 on the xy plane, and then theta ranges from 0 to 2 pi. If we evaluate this integral, we'll get 16 pi, and since our final answer is twice that, we get a final total outward flux of 32 pi. I hope that this video helped to summarize the concepts behind surface integrals as well as how to calculate surface integrals. We started by looking at surface integrals and examining how we can use projections to convert them into double integrals, which are easier to calculate. We also looked at using symmetry to solve surface integrals simply by directly calculating the normal vector and the element of surface area if we can take advantage of symmetry. Thanks for watching!